Hello, this is Jack Hicks, and this is my lab report for Physics 2211 Lab 5, which I did on collisions. So, as an introduction, the objectives of the lab were to observe and analyze a video of a system which includes colliding objects as well as obtain position and time data of the two objects colliding from the experiment. And then after this, we can compare the final and initial kinetic energies of the objects of the system and determine the nature of the collision, whether it's elastic or inelastic, and also determine if conservation of linear momentum was observed. All right, so the main ideas in this lab are the energy principle, which is that a change in an object energy is determined by the work done on an object in a system, and that the energy is also equal to the sum of all individual energies, as well as conservation of linear momentum, which says that during a collision, the total linear momentum of a system will be conserved. And there's also inelastic versus elastic collisions, which is that elastic collisions occur when there is no change in kinetic energy before and after a collision, and inelastic collisions showcase a change in kinetic energy. Now, these can be calculated through translational kinetic energy, rotational kinetic energy, which also includes the moment of inertia of a solid sphere, which is applicable in this experiment. So, as a little preview of the lab, the collision was found to be inelastic, with the initial and final kinetic energies not being the same, and total momentum before and after the collision were found to be close, but not the same due to experimental error. Now, the system in the surrounding were the two balls, the earth, the table, and pretty much everything, and nothing was in the surroundings. But what models are we using? So the models are basically just Newton's second law and the energy principle, specifically the energy principle. So we found the velocity of the balls right after and right before the collision and used them to calculate the respective total kinetic energies to see if they were conserved or not. And we assumed no air resistance or friction, and we set the origin at the initial position of the first ball. All the equations used are down below, which I'll go into more detail later, but on the right are all the known values, being the mass of the balls, the radius of the balls, the initial velocity, the initial angular velocity, and the initial x position of all the balls. Now, initially was right before the collision, and the final state was right after the collision. Now, getting into the actual experiment, here's a video of the experiment. So here's the actual tracker data. As you can see on the left, there's the video with the origin, the calibration stick, and the position of the masses. And then on the right are the actual graphs of the position of the masses, mass A and mass B, mass A being the first ball and the mass B being the second ball. So there was no coding in this lab, so instead I'll go into detail about the calculations of the kinetic energies and the momentums. So in order to calculate the kinetic energy using the tracker data, first we had to calculate the velocity, being the second x position minus the first x position over the second time minus the first time. And then using this, we could calculate first the translational kinetic energy initially and finally, being just 1/2 mv squared for each ball, and then before and after the collision. And as you can see, the final calculations are done below. So since the balls were rolling, we could also calculate the rotational kinetic energy, but first we had to calculate the angular velocity, being the velocity we calculated before, over the radius of each ball. And then we could use the equation 1/2 I omega squared for each ball, and I being 2/5 mr squared for each ball. So putting all those in the equation, we could calculate the initial and the final kinetic energy of rotation. So then finally, just to calculate the total kinetic energies, first the initial total kinetic energy was just the initial translational kinetic energy plus the initial rotational kinetic energy, and then the same with the final. Now, delta K is K total F minus K total I, which was seen to be negative 0.011976. Basically, this means that Kf was not equal to Ki, delta K was not equal to 0, so the collision was inelastic. So to calculate the total momentum, both initially and finally, it's just m1v1 plus m2v2, except the velocities are initial and final respectively. Now the final momentum was seen to be negative 0.0921 kilogram meters per second, while initially it was negative 0.07497 kilogram meters per second, which are different, slightly different, not much, but still different. So let's discuss the data. So looking at the data, the first ball traveled forward with pretty much a constant velocity till it hits the second ball, which then decreases ball one's velocity, getting much closer to 0. And then the second ball is stationary until hit by ball one, which then gives ball two some sort of velocity. Now the change in kinetic energy being negative 0.011976 joules means that the collision was inelastic, which was as predicted because that's the same as virtually all macroscopic collisions. Now, the initial momentum and the final momentum were different, which is not by much, but there was a very small change, which is not really possible, which means there must be some sort of experimental error because the predicted was different than the actual. Now, the error could be that I didn't take into account air resistance or friction, or that the balls did not roll in a perfectly straight line, or that there were rounding errors or experimental errors. So for some additional questions, what does it mean for a collision to be inelastic? We already discussed this, but it's basically just kinetic energy is not conserved. But why would this not be conserved? Basically because of dissipative forces such as friction or air resistance acting on the system. Now, what if the collision were elastic? What would the experiment look like? Basically, it would look the same. You wouldn't be able to tell without calculating the individual kinetic energies.